Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's my pleasure to introduce Parag Singla. He's here to talk about Markov Logic. He actually interned for me a few years ago in the summer of 2006? 5? I don't remember. Anyway, 6. And he worked on some really interesting work dealing with messenger data and search and doing a bunch of data mining and everything that would have been a lot simpler if Cosmos had existed. But anyway, he's come back to tell us about what he worked on during his thesis work under Pedro Domingos at the University of Washington. So thanks, Parag.
Thanks, Matt. So is the title of my talk, Markov Logic, Theory, Algorithms, and Applications. So most of it is joint work with Pedro Domingos, who is my advisor at university. There is some stuff that I worked in Kodak Research in Rochester. So I'll mention when that comes and who are the collaborators. So here is a brief outline of my talk. I'm going to give some motivation, the work that I've done, give some necessary background on Markov networks and a little bit on first-order logic. I'll describe Markov logic, on which I sort of will build on. Then I'll describe inference and learning algorithms that I've developed for this language, describe a couple of applications, and then conclusion and future work. So coming to motivation, it has been seen that in an area of science, there is this idea of applications and infrastructure, and this middle interface layer, which sort of separates applications from infrastructure. And it has been observed that whenever you have this interface layer well defined, separating the applications and infrastructure, the progress really happens fast. So what do I mean by that? So let's take networking. On application side, you have www, email, and everything, all the applications that you can think of, things like these days YouTube and other stuff. And infrastructure essentially consists of protocols, routers, and all those things. And interface layer is internet. So how does internet help? Is that applications can be developed independent of how or what's going on in the infrastructure layer. You can develop applications just knowing about the internet and optimize those. And similarly, infrastructure layer can sort of work independently. People can optimize the routers, protocols, and those two, as long as they interact well with the internet, everything goes sort of fine. And note that instead of making n square combinations between the applications and infrastructure, you have only order of n connections. So this really helps speed up the progress. Similarly, in databases, we have applications like enterprise resource planning, online transaction processing system, CRMs, and infrastructure is query optimization, transaction management. As you can see, both sides can develop independently. Applications can go on, infrastructure can be optimized, and the interface layer, as we know, is relational model. Once we have the relational schema in the mind, then everything sort of works well. And again, the progress can go on in both the directions independently. So what is the interface layer for AI? Applications, as we know, there are many: robotics, vision, NLP, planning, multi-agent systems, and many more. And infrastructure is essentially representation. How do you do the learning, inference algorithms? And what is the interface layer that we are looking for in case of AI? So for quite some time, people thought that first-order logic could be language of choice because it has the power to represent objects, relations among them, can handle very complex world scenarios. But the problem with first-order logic, as we'll see, is that it's very brittle. It doesn't have the power to represent uncertainty, which is inherent in the world. So we certainly like to have that. So that brings us to graphical models, something like Bayes nets or Markov networks, which have the capability to handle probability explicitly. But then the problem with them is that they do not really handle objects and relations. So you lack that capability of having that complex structure in the language. How do you do that? So that brings that what if we combine sort of these two approaches, the statistical and logical AI. Statistical, as I said, sort of the graphical models kind of approach, and the logical being something like first-order logic. So if we could combine those, maybe we could have something which could basically be a potential interface layer of AI, really speeding up the progress. So there has been this whole area of statistical relational learning which has come up, and this is sort of the background. There have been many languages which have been proposed, and today I'm going to talk about Markov logic, and in some sense maybe try to argue that it really gives you the representation power to handle both uncertainty and also the complex structure, and also has the engine where you could do fast inference and learning. Markov logic, as I mentioned, is not the first of these approaches. The The history goes back to 1986, probabilistic logic of Nielsen, and then many more models. And these could be classified based on what representation language they use to represent uncertainty and what kind of first order model they use. So I'm not really going to talk about those, but primarily focus on Markov logic, which was proposed by Matt Richardson sitting here and Pedro Domingos back in 2006. So briefly, in one slide, so for Markov logic, the syntax essentially is weighted first order formulas. So very simple. If you know first order logic, just write first order formulas, and that is the syntax. And semantics, as I'll explain it a little later, it can be seen as constructing templates for underlying ground Markov networks. In terms of inference, there have been a lot of algorithms that I have worked on, some of my colleagues have worked on: VOXSAT, LazySat, MCMC, MCSAT, belief propagation, lifted belief propagation. And I'm going to talk about some of these. Learning, you could use something like LBFGS, voted perceptron, or second order methods which have been developed. Applications, there are many, and I'm going to talk about two of them. And this slide, the red ones really highlight the algorithms that I've sort of worked on. There are a couple of others I've worked on, but I'll not be talking about those. So the red ones are essentially those that I'm going to talk about, in addition to, of course, explaining the semantics and the syntax of Markov logic. So this gives the basic motivation of the work that I've done. Now a brief background on Markov networks and first order logic. So Markov networks, I assume some of you may already be familiar, are essentially undirected graphical models of data. So you have these nodes here and the edges between them, and the nodes represent some kind of, in this case you could say some kind of binary predicate. For example, if someone smokes or doesn't smoke, if someone has cancer or do not have cancer, asthma, cough, various diseases that they might have. And edge essentially represents that there is a direct influence of one node on another. For example, if you smoke, then you are likely to have cancer. If you have cancer, then you are likely to have asthma or cough similarly. And the way they define a distribution over this network or over these nodes is by having these potential functions which are defined over the cliques in the graph. So in this case, you can see there are many cliques. There is a three-way clique between cancer, asthma, cough, and also there is a clique between cancer and smoking. And an example of a potential function is that, for example, for all possible states of smoking and cancer, you have this real valued function. Actually, it needs to be positive. So you can have all these values, and the probability distribution is defined simply a product of all these potential functions defined over the cliques in the graph, and Z is a normalization constant. And intuitively, these numbers just say that what state of the world is more likely. For example, in this case, you can see that only the combination true false has a low value, which means that that state of the world is less likely as compared to other states. Okay. Equivalently, this model can be represented as a log linear model. So it's a sort of exponent of linear combination of feature functions. Again, feature functions are defined over cliques in the graph, just as before, but note that these can be much more compact than the potential representation. For example, in this case, you may say that this feature is on or 1 when smoking implies cancer. This small formula defined over these two nodes or variables is true, otherwise it's false. So instead of having 4 possible states, you can represent it much more compactly in this log linear fashion, and in this case W can be any real valued sort of weight. So I'll be using this form throughout this talk for defining the probability distribution, and Z is normalization constant as before. Okay. So this was Markov networks. So coming from the logical side of things, first order logic. First order logic essentially consists of constants, variables, functions, and predicates which represent your underlying world. Constant could be something like people in your domain, Anna, Bob. Variables are x, y, z, which instantiate over the constants in your domain. Could have functions like mother of x. So x, for example, Anna, then whatever the person who is the mother could be represented by this function. And friends xy, which is a predicate, which could ask, for example, which could be true if x and y are friends with each other, false otherwise. Grounding is an important construct in first order logic. It corresponds to replacing the variables in the predicate or any other construct by the corresponding constants. For example, friends xy, you could have friends Anna, Bob, and similarly for other constants. Formula essentially combines predicates. For example, smokes x implies cancer x, which is true when smokes x is let's say true and cancer x is true, and certain other cases. A knowledge base is essentially a set of formulas, and it's a standard rule of standard theorem of first order logic, that it can be equivalently converted into a clausal form, at least for the finite first order logic. And a world along with an interpretation sort of assigns truth values to all the ground predicates. So that is sort of the semantics of first order logic. So I will be using this. Now given this background, let us try to understand what does Markov logic do given Markov networks and first order logic. So the problem with first order logic that I alluded to earlier is that a logical knowledge base is essentially a set of hard constraints. So you really need the world to satisfy all the formulas. So even if a formula is false in your domain, then the whole thing sort of crumbles down. It's very brittle. For example, if you have a rule smokes X implies cancer X, and even if one person smokes but they do not have cancer, then the whole theory sort of crumbles down. So what if we could make them soft? That is, when a world violates a formula, it becomes less probable but not impossible. So that is the idea in Markov logic. And how do we do that? Essentially you attach a real valued weight to each formula, and the weight tells you how important that constraint is. Higher the weight, higher sort of that constraint is, and you better satisfy it. In particular, a probability of the world is now proportional to the exponent of weights of the formulas it satisfies. So more formally, a Markov logic is defined by two constructs, f and w, a set of pairs f and w. F is a formula in first order logic and w is a real number, and together with a finite set of constants it defines a Markov network with where there is a ground node for each grounding of a predicate, and there is a feature for each ground formula, and I will explain this with the help of an example, and w is the corresponding weight of the feature. So here is an example. Let us take this formula, a very simple domain, and I will be using this throughout the talk. So the first formula is saying that for all people smokes X implies cancer X, that if they smoke then they are likely to have cancer. The second formula says that if X and Y are friends and X smokes, then Y also smokes, that is friends have similar smoking habits. So this again may be brittle because these are very useful rules to model the real world, because most people who smoke are likely to have cancer, more likelihood of having cancer as compared to a normal person. Similarly, it has been observed in social sciences that friends tend to have similar smoking habits. So these are very good rules of thumbs but may not always be true. So let us convert them into Markov logic. So we gave some weights which could be learned using training data. So these are some arbitrary weights in this case. So what is the ground Markov network? So first let us say we have two constants, Anna and Bob. So we create the ground nodes. So we substitute Anna and Bob in the corresponding predicates, smokes and cancer and friends. So smokes Anna, smokes Bob, cancer Anna, cancer Bob. Similarly the groundings of friends predicate. Note that we need both friends AB and friends BA because they may mean different things. So these are all my ground nodes corresponding to ground predicates, and then I connect those nodes which appear together in any ground formula or ground clause. So smokes Anna connected to cancer Anna, smokes Bob connected to cancer Bob, and similarly for corresponding to the second formula I also create all the cliques. So this is my ground Markov network, and now you are in the domain of Markov networks and you could do various inference and learning on this. So that is the basic semantics, and of course I am going to talk about how to sort of make it efficient given this representation. So any questions at this point before I go further? Okay. So as I mentioned, MLN can be seen as a template for constructing ground Markov networks, and the probability distribution of a particular state of the world is given by Z being a normalization constant and Wk Fkx. So this is basically the form of Markov networks, Wk being the weight of the feature, and the summation varies over all the ground formulas in your theory. Fk is the kth feature and Wk is the weight of that formula from which this feature came. Equivalently, you can write it in this form. Because we have sort of binary features, so whenever the formula is satisfied, ground formula is satisfied, then it is on, otherwise it is off. So you can see that equivalently it can be written as a summation over first order MLN formulas and Wi Nix, where Nix is the number of formulas which are satisfied, because as many formulas are satisfied from that first order formula, that many times feature will be on and that term will be there. So this is the second equation is what I will be using throughout this talk. The distribution defined by Markov logic is defined by this equation. Okay. Now briefly, it can be shown that what is the relation of Markov logic to various statistical models. I sort of started saying that it sort of combines the power of uncertainty, various standard probabilistic models, statistical models with first order logic. So what is the connection? You can show that all these things on the left side, Markov networks, Markov random fields, Bayesian networks, and many others, hidden Markov models, conditioned random fields, they can be represented as a special case of Markov logic. In particular, you make all the predicates zero arity because you don't really need the variables, and then you can represent all these models. What is the connection to first order logic? So it can be shown that in the limit of infinite weights, when all your weights tend to infinity, the whole distribution is essentially the one represented by first order logic, so which is very nice. In the limit case, it tends to first order logic. But not only that, in the case when your knowledge base is satisfiable but the weights are not infinite, the satisfying assignments are essentially the modes of the distribution. So which again makes sense that the state which are most likely are sort of the satisfying assignments of your underlying theory. So which again makes sense and very intuitive. And in particular note that the difference between Markov logic and first order logic is that it allows contradiction between formulas and still give you a reasonable probability of the underlying world. And one thing I will just mention, not go in detail, is that I did not talk about really how do you represent infinite domains, which is essentially the basic one of the key things that you can do with first order logic. So we had this paper at UAI where we extend Markov logic semantics to infinite domains, and it turns out that it's not that straightforward, but you can do it, and we borrow a lot of ideas from physics literature. In particular, we use theory of Gibbs measures, and you can show that as long as your underlying network, each node has finite number of nodes, then you can have a valid distribution which can be represented as an infinite collection of finite distributions. So I'm just not going to talk too much in detail about this, but you can look at the paper if needed. Okay. So now, having described sort of the representation language, I'm going to describe how do you do inference, in particular efficient inference in this kind of model. So inference essentially corresponds to the problem of finding the probability of query atoms given some evidence. So probability of y given x, where y is your query atoms and evidence could be something that you know at the time of inference. So substituting it back into the formula for Markov logic, you get probability of y given x, which is essentially 1 by zx. Note that normalization constant now depends on x because x is fixed, and essentially you have the formula for the distribution wi ni xy, I varying over all the formulas, all the first order logic formulas in your theory. So but the problem with that is that you have to compute this normalization constant, which is takes exponential time, so you cannot really do it exactly, so you have to resort to approximate methods. And you can use, there are two different ways, I mean there is one more, but primarily you can say there is MCMC, that is Markov chain Monte Carlo. So you can set up a Markov chain and then sample from stationary distribution. Other way which has become sort of more popular in last few years is belief propagation. Here the idea is that you form a bipartite graph of nodes and the factors or the variables and the features, and then you pass messages from nodes to features and vice versa, and you repeat until convergence. So I'm going to focus on the second one and show how you could use this to do inference in Markov logic. And there is another approach, variational approaches, which again I'm not going to talk about in this talk. Okay, so belief propagation. So the idea is that you pass these messages vice versa from nodes to features and back, and what the messages represent are essentially the current approximation to the node marginals, and you initialize each message to 1 and then sort of carry this back and forth. So I'm going to show this with an example. Here's the example. On the left side you have all the nodes and right side you have the features. So let's, can see that right? Yeah. So an example of a node or a ground predicate is smokes of Anna. So this is again the example that I've been talking about, the friends and the smokers domain, and the feature could be smokes Anna, friends Anna, Bob implies smokes of Bob, and all these nodes represent essentially the groundings of predicates on the left side and groundings of features on the right side. And there is a connection between those a node on the left and a node on the right if they appear in the same feature. For example, smokes Anna would be connected to the feature smokes Anna, friends Anna, Bob implies smokes Bob, and then you want to pass messages along these edges as you go along. So what are these messages? So this equation gives the message passed from the nodes to features. There is a lot of notation here, but the message is very simple. What it is saying is that it takes all the messages that this node received from the features in the previous time step and multiplies them together and sends it to the feature that it wants to send. So you multiply all the messages that this node received except for the feature being considered, in this case f, multiply them and then send it to the feature that you want to send the message to. And intuitively what it is saying is that what is the current belief that node has about its probabilities, about the probabilities of being in various states. Similarly, the message from the features to nodes is slightly more complex, but the form is similar. So if you look inside the summation, the inside term is similar, that you multiply out all the messages that this feature node received from the nodes in the previous time step except for the node being considered. Then you multiply out by the feature or the potential, that is e raised per wfx, the potential at this feature, multiply all of them together, and then you sum out everything except for the node being considered, and then you pass it back. So this is the standard sort of message passing in belief propagation, and it has been shown that if this is not guaranteed to converge in the loopy graphs, in tree it converges and gives you the right result. In loopy graphs it's not guaranteed to converge, but for many problems it is a very good inference algorithms, really gives you good results in very fast time. So this is nice. We could use this by converting the Markov logic into the ground Markov network, constructing this graph and then passing messages. Yes?
When it doesn't converge, do we have any bounds for stopping it?
Right, yeah, that's a good question. Yeah, I think there are bounds, but many a time what people do is just run it for a few iterations, certain number of iterations, and then sort of stop. Yeah. So this is nice, you could use it, but then there is a problem. The problem is that the kind of domains that we are going to work on, and I will show some examples, that there could be easily billions of features, because consider simple theory, smokes x implies cancer x and friends xy. Even if you have, let's say, 1000 people in your domain, already you have 1000 cross 1000 features, and then this really grows exponentially with the number of variables in your features. And that means too many messages, the network size is too big, and then you have to pass too many messages. This could be really taking a lot of memory and really too slow. So what is the solution? So the solution idea that we propose is that instead of passing that many messages for each ground node, what if we could cluster those nodes together which pass the same message in the ground version. So if you could somehow identify those nodes which would have passed the same message during the BP, then we could pass only one message for the whole cluster, and that could really reduce the number of messages which are passed and really make your algorithm much faster, also reduce the network size. I'll try to demonstrate this on the example that we've been looking at. So this is the original ground BP. You have nodes and features and passing the messages, and let's say somehow you identify using these boxes, I have demonstrated that all the nodes which would have passed exactly the same message in each iteration of the belief propagation algorithm. So let's for now assume that somehow we identified those, and I'm going to tell more detail how we do that. But once you know that that is the case, then actually instead of having all these edges between the nodes on the left and the right, you could have essentially one edge between each box. So as you can see, the number of messages just could reduce by big amount in this case, because in this case you have only 3 messages going back and forth between both sides, and it will give you exactly the same result. And the form of messages is exactly the same except for 2 constants, which are essentially the number of which are the function of the number of edges which went through those boxes. So note that we replaced many edges by one edge. So we have somehow we have to take into account how many nodes were clustered in one box, and these alpha and beta constants essentially depend on that. So other than that, it's exactly the same algorithm, runs in the same way, gives the same result, and will be much faster and can save you a lot of memory. So now I'm going to describe it in more detail, how to actually find these boxes and what these messages are. Okay. So basic idea in lifted belief propagation, you can see as 2 steps. So the first one is lifted network construction, that is construct these boxes which we call supernodes or super features. The name should be intuitive. Supernodes formally is the set of all ground atoms that all send and receive the same message throughout the ground version of the belief propagation algorithm. Similarly, a super feature is defined, all ground clauses or formulas which send and receive the same message throughout BP. And then you construct this network, run modified belief propagation with those alpha and beta constants on this network, and as I said, it gives you same results as ground BP, and memory and time savings can be huge. So how do we construct this network? It's a simple process, it's a 4-step process. So we sort of start with initial guess for the supernodes. So given your domain theory and given some constants and evidence, what is the initial guess for supernodes? So very basic guess is that you want to cluster all true predicates in one box, all false predicates in one box, and all unknown predicates in one box. That is the first guess, and you will refine them as we go along. So given these predicates or supernodes, you can essentially now join them together to get the next level of superfeatures. Given that, you can project them back onto supernodes to get the finer supernodes. That is, you project the superfeatures down to ground predicates, and all those predicates which appear in the same number of superfeatures will now be clustered together, and this is repeated until convergence, and this algorithm is actually guaranteed to converge to the optimal network. So this is the algorithm, and I will demonstrate this with the help of an example. Example is this. So I am just going to work on one formula, and then you can extend it to as many formulas as you want. But for illustration purposes, just one formula. Let's say we have smokes x, friends xy implies smokes y, the same old example. Let's say we have some piece of evidence, that is Anna smokes. We know that smokes of Anna is true. We know that Bob and Charles are friend, and Charles and Bob are friend. So this is our evidence. And let's say we have n people in the domain, and n being greater than 3. So intuitively, it's very clear that the boxes that you should get, the algorithm should give in this case, is 3 boxes: smokes of Anna, smokes Bob Charles, and smokes of all other people. Because Anna is sort of different from all others because she smokes, so probably the probability for her should be different from others. Similarly, Bob and Charles are different because we have some extra piece of information about them, and all other people should come in one box. So this should be my clustering of the supernodes. That's the idea. So let's see how the algorithm sort of discovers that. So we have this sort of now supernodes on the left and superfeatures on the right, and I am going to show how you sort of refine them. So the initial set of supernodes are simply, you create the supernodes for true, false, and unknown case. There are no false predicates, no false evidence in this case. So we have smokes of Anna, which we know is true in the green, smokes of X for all people other than Anna, which is unknown. Then friends Bob Charles, friend Charles Bob, which is true, and friends XY for all other people. So these are my initial 4 supernodes. As I said, you don't really need the box for false case because there is no false evidence. So given these initial supernodes, let's try to construct superfeatures. So we are trying to construct the superfeature smokes X and friends XY implies smokes Y. So note that smokes Anna, and the color coding sort of tells you where those nodes are coming from. So smokes Anna comes from the first supernode. Then you join it with friends Anna X and smokes of X. So this is my first superfeature coming from the boxes on the left side, just simply doing a join just like in databases. Similarly, you could construct other features, other superfeatures, and the color coding again demonstrates where those supernodes came from, and third one and the fourth one. So you can show that these are the only non-trivial combinations in this case. So you got all these 4 superfeatures corresponding to the 4 supernodes on the left, where you really just did the join. So now, having constructed these superfeatures, let's see how do I construct the supernodes. So I again used a different color coding for each superfeature, and what we want to do is project them on each ground predicate, that is smokes of Anna, smokes of Bob, and whoever there is. And there is this box of 4 counts. Each count is for each superfeature, and we are going to populate this with the number of ground features which projected on smokes of Anna. So populate with projection counts. So note that the first one projects n-1 times, because X can take n-1 possible values. In this case, X cannot be Anna, so it projects n-1 times on smokes of Anna. So I got n-1, and you can show that the second one projects 0 times, because smokes of X cannot project on smokes of Anna because X cannot be Anna. Similarly, get 0. Smokes Bob cannot project on smokes of Anna. Similarly, smokes Bob cannot project on smokes of Anna. So we get this count. Similarly, we do it for all ground predicates, and we cluster those predicates together which got the same count. So in this case, I have already sort of clustered Bob and Charles, but you can verify that they would have got the same count, 0, 1, 1, and -3. And since they got the same count, they are indistinguishable from each other at this step of BP, at this step of the network construction, and you combine them together. And all other things will now combine into the final box, because they have the same counts for all the superfeatures. So you sort of now you have the new supernodes, you join them together and then get the new superfeatures, and vice versa. In this case, you can show that this is sort of the final step, and if you join them one more step, you will get the final superfeatures. And you can show, more importantly, you can see that you have discovered the intuitive clustering of nodes, that is smokes of Anna, smokes Bob Charles, and smokes of all other people. So that is what you are looking for. So that is basically the lifted network construction algorithm. And we have a theorem, this appeared this year in AAA, this paper, and we show that there always exists a unique minimal network, and our algorithm LNC, lifted network construction, finds it, and running BP on this network essentially gives you the same result as running BP on ground network. Now experimental results, so in the paper actually we have results only on 3 domains, but I am working on a journal paper, so I have results on many more domains. So there are 6 domains that I am going to present results on. The first one, entity resolution. I think many of us might be familiar with this. Given a database, I am going to talk a little bit more about it. Given a database of records, you want to identify which of the entities refer to each other, which of the references refer to the same underlying object. That is the problem of entity resolution. Link prediction. So we have this data set of professors, students from university, UW, and we have the information like who TAs which course, who is a professor, who is a student, and we want to find out who is advised by whom. And then there is this data set of protein interactions from biology domain, and we want to find out which proteins interact with each other. Hyperlink analysis, this is basically you want to find out which page is which web pages link to each other given the information about their topics. Image denoising, this is on image domain. So you have a binary image, there is some text in the foreground and a background, and it is randomly, there is some noise in the image, and you want to really separate out the noise. And then finally the friend and smokers domain that I just showed. So here are the results. There are 3 times, this is on time, so I am comparing the ground version and the lifted version. So there are 3 times, the construction time, BP, and total. So construction time is the time taken to construct the network. BP is how much time it takes to run the belief propagation algorithm, and the total time is essentially the sum of these 2. So as you can see, the ground time in almost all except for maybe couple is more in the case of lifted case, and that makes sense because you have to construct all these super nodes and super features and then sort of combine them, so it takes some time, and the ground version is faster because you can just ground out the network. But note that now BP time is much less in all the cases because the network is much smaller than the ground network, and it can be much faster. How big are these datasets? So Quora, for example, is about 1000 records, so 1000 cross 1000. Of course, we use something like canopies. UW CSC is also about I think few thousand. Maybe Matt can correct me. Few thousand features, right? Then others are also probably similar size. Image is much bigger because you have 400 cross 400 pixel image, so it's probably bigger. Yeah, yeah.
Well, how many predicates do you have then? Do they vary much in terms of the cardinality of the predicate set?
You mean like what? How many variables in each predicate? I think at most we have 2. There are few in UW CSC which have 3, like publications or TA, professor, student, and course. But most have 2 or 1, just like the smokes example.
And what's the size of the knowledge base for each one?
Like number of rules? It is up to 100. In some cases it's only 2 or 3 rules, like for example image domain we have just 2 rules which say that one is that whatever value is observed you are likely to have the same real value. If observed is text, then it is text, and the second rule says that you are likely to have the same value as your neighbors. UW-CS is more about 94 rules, so it varies across that. Yeah, more questions?
So the friends and smokers domain, how did you make the network for that?
Right, yeah, so I did not explain that. So essentially what I did was I had this sort of, I decided number of people, how many people I want to have, and then sort of randomly chose whether they smoke or do not smoke, and then also use sort of a random sort of distribution. I forgot the exact details, but the idea is that you sort of have clusters of people, and for each cluster you decide whether you want to have a friend's relationship between them or not. That was the idea.
So I have a more general question. I don't know if this is a good time or not. So it seems like the technique, it works best when the domain like breaks into little pieces, right?
Exactly.
So does it require, like, to what extent do they need to break up? I can't think it through quickly enough. Like, does it need, like, would the ground Markov network have to have completely separate disjoint clusters, or would it can it do better than that?
Oh, I think it does much better than that. So I think the idea is basically like looking at this example, that it doesn't really say in this case, for example, right, that Anna, Bob, Charles and all others, they are independent, they'll certainly be connected. It's only identifying that all these nodes could be treated in one cluster, that is they would be behaving similarly with respect to the cluster. So suddenly there are all interconnections. I'm not saying that your graph is disconnected. So that's a very important point actually. That graph is completely connected in the general case, right? But what we are saying is that all these nodes essentially would have behaved in exactly the same fashion. So why don't you just pass one message instead of passing, let's say, n messages? And that is the key to the algorithm.
So in the Smoker's Friends one that you generated, does it end up being each supernode is sort of each supernode is a different number of smoking friends? Effectively.
Right, so I did not exactly look at what were the clusters, but basically similar idea, right, that people, all of those people who had, let's say, same smoking evidence and also who were connected to, let's say, same number of friends, right, would have the same evidence of being the ground thing. It may split a little bit further because evidence may propagate, but we realize that actually it doesn't really split further, and I'll show it in the example actually. Yeah.
One more quick question. So, if I understand this right, it grows essentially polynomial with respect to the number of the arity, right? So if you have, like, say, 1,000 proteins that you're interested in, right? You have some predicate with arity 3, then you have 1,000 to the third to make predicate
exactly.
4. So it is going to grow that way.
Exactly. Yeah. It's
message passing is what we've optimized down here, right?
Right. So we are optimizing both, right? Because we are trying to optimize also the ground features. Ground features will be 1,000 to the cube, but the lifted features or the super features will be much less.
But you will still need to calculate every single ground feature first before you go to optimization, right?
Right. Yes. So yes, that's a very good question. So actually, yeah, I kind of skipped that detail, but it's a very good question. So what we do is we do not really construct the ground features also. So what we do that is that, let's say you start with let's say smokes X, cancer X, right? That example. So what we do is initially we do the ground. We construct all the ground predicates. So up till that point it is true, right? But then we sort of cluster them, and when we do the join only on those. So you do not really need to construct the ground features, all the ground features, because now you have a compact representation for the ground predicates, and you can join them using that compact representation. And then you can do even more optimizations, things like, suppose you know that most of the things are false, so you do not even need to look at that explicitly. You can just do anything which is not true and unknown is false. So you do not really need to represent that. Yeah. Does that answer your question?
Yeah. So okay. If you do that for the smoked example, if you had 1 million people, you'd have 1 million squared initial grounds you would have to address, and then you could actually proceed to optimize them out, right? For you friends, for instance, right? You'd have to do friends with every single combination, right?
Right. So I guess what I'm saying is that, let's say you had a lot of people, and let's say you knew that most of the friends XY are unknown. So you do not really explicitly need to construct those, because what you could do is construct the compact representation for true and the false case, and everything unknown is sort of default value, and that essentially you do not, it's just like the closed world assumption in databases, the same thing. Yeah. Right, so these are the results, and you can see overall lifted BP is much more powerful than the ground version. In some case it's phenomenal, for example WebKB, because what we are doing is essentially, in this case, this is sort of a simple example, we are not using the words information, we are just using that certain topics imply that certain probability of being linked to each other. So if there are 10 topics, about 10 squared possibilities are there. So the super features are really big, as in like they have a lot of ground nodes clustered with them, and it runs really fast. So you don't really need to construct the whole network. And this is, so BP does not always converge, but results are pretty good even in all the cases, and this is after a run of 1,000 iterations, 1,000 BP iterations. And as I said, the results are exactly the same in the ground and the lifted case.
Did you compare the accuracy of the BP versus sort of MCMC?
Right, so I did that. I do not have those results here, but they are quite comparable. Yeah, they are quite comparable. Yeah, and this is the number of features and physical memory. So I think that may answer actually some of the questions that were asked. As you can see, that the number of features is certainly much less in case of BP. That may not directly translate to physical memory saving. I think that is a valid question that you raised, because many times you have to actually construct the ground network. But as I said, many cases, because of the compact representation from the very beginning, you can in fact save a lot of memory, and I think in almost all the cases we do have a lot of memory gains. I should point out that for UW CSC and image, what we did was running the network construction till end actually used more memory. So I stopped at after 3 or 4 iterations of lifted network construction, which gave exactly the same results and which runs much faster. For all other domains, I ran the lifted network construction till end, but for these 2 domains, the results here are after stopping the construction after 3 or 4 iterations, but it gave exactly the same results. So,
can you construct cases where your proposal is no better or even worse in either time or space than the baseline?
Yes, that could happen, yeah. In worst case, that could happen, because if you have to ground out the whole network, although I'm not sure how common will that be in general, but if you have to completely ground out the network, then you'll spend extra time really constructing those super nodes and super features, only to realize that you had to actually ground out the whole network. So it will be a little slower.
It could be a little slower, and space-wise it would be no worse?
Space-wise, I think it depends on your representation. If you have a very good representation for super nodes and super features, yes, it should basically be the same. But yeah, in any ordinary implementation, it could take a little bit more space because you have to represent those super nodes and super features. Okay, so finally, this is sort of the last result on this. I think again this kind of goes back to some of the questions that I think Matt asked. That I also sort of experimented on this. That how does lifted network construction vary when I increase the number of objects in my domain? So note that in friends and smokers, as I vary the number of people, the lifted network size remains about the same, because essentially the number of clusters is the same. The ground version, it's on exponential, sorry, it's on log scale, so number of features is on log scale and I have number of objects. So you can see the green curve sort of grows with the number of features, but the red curve stays constant because the final number of features that you have is essentially the same. So this is again a nice property because your domain is getting bigger, but the final number of features that you have is essentially the same.
Is the red curve for linear if you have the y-axis linear?
The red curve is almost linear actually.
Okay.
Yeah.
So, I mean, but given your model of generating that
Yes, exactly. Yeah, because I'm using the same model, which means that more or less the nodes finally there are only a fixed number of clusters in which they would fall in, and then yeah, exactly. Okay, so I think in interest of time, probably I'll skip the learning part. Basically, there's some work that I did on how to learn the parameters. So I guess I'm done with the lifted BP part, which is sort of the crux or the main sort of idea, one of the main ideas. I'll skip the learning part. Basically, how do you learn the parameters in Markov logic, and we had a paper on that. But you could talk to me after the talk. Yeah. So I'll describe a couple of applications that I use Markov logic for doing. The first one is.
Sorry, can I interrupt? One question about the learning. Was the learning that you did independent from the lifted BP inference stuff, or are they tied to each other?
Right, so that's a good question. So it happened, at least chronologically, that I worked on the learning before the lifted BP. Okay. So that was independent in that sense. But now, since we know how lifted BP works, since learning uses inference as a sub-step, so we could use lifted BP within that to use the learning.
Right. And learning can also work with the other, like they're independent.
They're independent. So you could plug in any black box for doing that inference step within the learning, which could be lifted BP. Okay. Yeah. Okay. So applications, I'll describe 2 applications. The first one is entity resolution. I briefly talked about this. Data cleaning and integration is first step in data mining process. And when you merge data from a lot of sources, typically result in duplicates. You want to resolve these duplicates before you can do sort of any effective data mining. For example, if you have papers from different domains, the authors may be spelled differently, titles may be missing, venues may be sort of abbreviated. So you want to resolve them before you can do any sort of effective data mining. And entity resolution is this problem of identifying which records or fields refer to the same underlying entity. This is a very well known problem in literature, and the original model was proposed by Feleghi and Sunter back, I think, in 1960s. And they had a very simple model. The idea is that you make each pair of decisions independently. So you take each record pair and you find out the similarity between those attributes, and you see if the similarity is more than a threshold, then you declare it a match, or otherwise a non-match. And there have been many improvements on the original model, but most of them actually make this pairwise independent assumption that they can be resolved independent of each other. But over the time, people have realized that it helps to incorporate dependencies into account. Resolving one pair will help resolve another pair, and this is what we sort of incorporate. But the problem with these approaches is that even though they take they take dependencies into account, the problem is that all these approaches, different approaches, have been developed as standalone systems, and they address different aspects of the problem. So there is no sort of unified solution to all this, which I'll try to present using Markov logic. So we presented this, appeared in ICDM, and the idea is simple, that you use weighted first order formulas to give the domain theory, and then for each formula you have the rule which sort of tells you how important that rule is. We used some hand coded rules, but you could always learn them using structured learning algorithm in Markov logic, and it combines many previous approaches very seamlessly. In particular, there was approach by McCallum and Wellner which introduced transitivity between different pairs. You can write just one formula for transitivity in Markov logic. Similarly, we had one approach which sort of combines them, and any more new approaches can also be combined into this framework. So this is the sort of the example which will demonstrate the power of sort of doing this, you building a collective model rather than doing them independently. So this is a citation example. So you have author, title and venues. So you can see that intuitively a human can figure out that the first 2 citations refer to the same paper and the last 2 citations refer to the same paper. But the problem is that the first 2 pairs are reasonably similar to each other. The authors are similar, the title is similar, and venue is not similar, but then maybe you are able to say, okay, venue is just abbreviated because authors and titles match. So you may be able to say that. So this is just a correspondence between the titles and authors and venues. So you may be able to say that the first pair match. But now note that the second pair is more problematic because one of the authors is missing. The title is really worded very differently, and also the venue is abbreviated. So the threshold may not be high enough to declare it as a match. But once you identify that the first pair is a match, you will know that AAAI and American 21st National Conference on Artificial Intelligence is the same conference, because you know that they are the match, therefore the venues are the same. Once you have this information, you could really use this to deduplicate the second pair. So you could, once you know that AAAI and this string is the same conference, this pair also appears in the second case, and then you can combine them and use this extra information to now say that they are actually the match. So this is the basic idea of doing this collectively, and we give a model based on Markov logic, and we write first order rules as I described. Again, I'll skip those, I'll not go in detail, and as I said, you can really write a domain theory using Markov logic, which sort of combines all these collective approaches. And we did some experiments on Cora and WebServe 2 citation datasets, and we show that collective features help improve performance, but more so we showed that many of these previous approaches can be seamlessly combined using Markov logic, in many cases writing just one formula for the previous approaches for which the whole system was developed for just one approach. Again, I'll be happy to talk about in more detail. So finally, the second application, this is relating to, so this is actually the work that I did at Kodak Research with Henry Couch and some of his colleagues. So this is about predicting social relationships in consumer photo collections. So here, Kodak being sort of a photo company, the idea was that can you use something like Markov logic to build smart cameras. So let's say you have a bunch of pictures of a user and you want to identify various social relationships in the pictures that the user took. In this case, for example, the picture in the left picture, this person may be interested in that he wants to say that go look at all my pictures and find out what kind of kids are my children hanging out, if they are in bad company, if they are in good company, or what sort of kids are they hanging out. So at the outset you may say it's a very difficult problem, you don't know what his kids are, what other kids are, and how do you do that. But if you just show these 2 pictures to a human, he or she may have a very good guess that the kids in the left picture are probably his own children and the third kid is not his child. Why? Because we know that typically children tend to be photographed with their parents, whereas friends appear together. So the kid only in the left picture probably is friends of these 2 kids, and these 2 kids probably belong to this person. But again, we are not sure, but these are like sort of good rules of thumbs. Similarly, you could have other rules of thumb saying that friends appear together, parents are older than their children, which is sort of a hard rule. You could say that relatives appear together with each other, grandparents like to appear with their children, and so on. So you could write various rules which again are not always true, but which give a very good information about the underlying domain. So we constructed, we handcrafted an MLN which had about 5 hard rules saying like parents are older than their children, and 14 soft rules as I mentioned, and the rules, the weights of the soft rules were learned using some training data that we basically had some volunteers at Kodak, about 13 different people. So they labeled their photographs with relationships that they had. So we asked them to label, and there are about 4,800 total images. And what we wanted to do was predict 7 different relationships: parent, child, spouse, relative, friend, child, friend, and acquaintance. So I should mention that for this problem it was sort of an initial venture. So we assumed that the face recognition has been done. So which is face recognition and also the identification. So which is again a big assumption, but as you can see that you can think of constructing a bigger model where you want to fold this in as a part of the model. But for this, the results that I am going to show, we assume that we know what the faces are, and we just want to identify what the relationships are given those faces. And we compared 5 models. So since nobody at least in the published literature has done this before, so we compared very basic models. The first one was random, so you randomly predict each relationship with uniform probability. Then prior, so you predict based on prior information in the data. For example, if most of the persons appearing in photographs are kids, so you give more probability to the child relationship. Then hard constraints, so you can have only the hard rules. For example, parents are older than their children, can combine hard and prior, both of them together. And then the MLN, the full blown MLN model with all the soft constraints and the hard constraints and the rules learned for the soft constraints. So these are the results. So this is precision recall curve. I am comparing all the models. So as you can see, all of them are pretty low, which means that it is a hard task, but still you can see the red curve dominates all those curves. And more interestingly, the random curve is sort of at 0.14, which is sort of the baseline, right? There are 7 relationships, so 14 into 7 is about 198. And then each sort of additional model gives you more and more information. The prior is better, then the hard is even better, hard prior is better, and the MLN sort of combines all them and adds some extra power to give you sort of the best model. And as I said, this is sort of the initial experiments we did. Certainly you could try to improve the model. We did not really learn those rules, so you could use training data to learn those rules, and then that could even maybe improve the results. So this was the second application. And just to mention a few, these are some of the other applications. Most of the applications people at UW, at some other places have been working on: information extraction, and many of those actually papers have been published recently. Link prediction, collective classification, and many others. I'll be happy to talk about some of these after the talk. And I mentioned just a couple of those which I've worked on. So, and finally, all this has been developed using Alchemy software, which has been developed at University of Washington. There are many authors besides me. It gives the whole first order logic semantics of Markov logic, has the inference algorithms that I just described, also has structure learning to learn those rules. This is the website. And finally, conclusion feature work. So in conclusion, I tried to sort of present that unifying statistical and logical AI is an important aspect which could really progress speed up the progress in AI, sort of providing the interface layer. Markov logic could be one potential choice. It's a combination of logic, very simple and powerful models, various algorithms I presented for efficient learning and inference. I should definitely mention that there are many more learning algorithms and inference also, which probably I did not really get time to talk about. Many applications. And finally, coming to future work, so there are many directions, but I'm interested more in generalizing the framework for lifted inference. So how could you extend the lifted BP framework to other algorithms like MCMC? Already I'm working on how to sort of give a general framework for VE and BP, variable elimination, which is exact, but also extending it to MCMC, then also connection with resolution. So we have this resolution approach. So what is the connection of lifted BP with resolution in first order logic? How you could use this in potentially infinite domains. And the third one is that identifying substructures in network for efficient inference. So here the idea is that it could be possible to break up your network in various parts where the inference in some of the parts is really simple. For example, you could have a linear chain in most of the network which you could, for example, solve using something like Viterbi, but some part may be complex. So could you really combine those two to basically do inference separately on those parts and then combine those results. So that could be one potential approach for doing fast inference. So in general, I am interested in a little bit longer term in developing a comprehensive theory of lifted inference and of course learning, because that's a sub-step for learning. And the intuition that I have is connection with human perception. For example, let's say if a human being is taken to a new place and he or she is asked to open his eyes for a second and then close it and then asked that what did they see. So they could say that, oh, I saw some very big buildings and there is a parking lot on the left, but they may not be able to tell more. Now let's say if you ask them to open the eyes for 5 seconds and ask them what did they see, they could see, oh, I saw 7 buildings and there were like 2 parking lots and there were like some cars here and then there were like a couple of roads. And if you gave more time, they could really now tell what were those buildings, how high they were, how many floors there were in, and so on. So can we do something similar for probabilistic inference, that given the time that you have, you could sort of start with a very crude approximation for the nodes, like the sort of the clusters that I provided, that start with very crude approximation, do some basic inference, and as you have more and more time, sort of refine them as you go along, and then depending on time you have, you could actually give the exact results if you have sufficient time. And then of course this has a lot of applications in computer vision, robotics, activity recognition, biological data, and so on. I think so that's pretty much it. Thanks. If you have any questions, I'll be happy to answer. Questions?
This is very high level. Is there any connection to junction trees in the way that you're doing lifted inference?
Right, so that's a good question. Yeah, there is actually interesting connection. I sort of refer to variable elimination. So I'm actually working on a paper which sort of gives a general framework, which very generic framework for having this idea of splitting the nodes to how does it tie to with VE, junction trees, and lifted BP. So the idea is similar, that in junction trees also you can sort of, I think it's easier to think in terms of variable elimination first. So the idea is similar, that you start with this, so you know about bucket elimination, there is a, so Reena Decter had a paper on bucket elimination which sort of gives a framework for variable elimination, but the idea is similar, that you have these supernodes. You start with the same kind of supernodes and you try to eliminate them, and at each elimination step you sort of see whether you really need to refine them or not. So you start with very crude nodes, and at every step of elimination you really see if you really need to refine them or all of them can be really just eliminated in one step. And this idea is similar to BP in that sense, and it turns out that it really helps. And you may have come to the talk of Rodrigo. I think he gave a talk here, lifted variable elimination, gave a talk, I think some of you probably were here. So that ties with his basically there is some stuff on lifted variable elimination that connects back. Yeah. Any other questions?
I have a question.
Yeah.
So when people are authoring these, you could easily add a rule that's going to suddenly make it take 10 years to do the inference, whereas before it was going to take a minute. I think similar problem in databases, right, where like you add a certain join and all of a sudden it's going to take forever. Do you think there's, is anyone looking at trying to estimate like how long a computation is going to take, or sort of giving some kind of feedback, like because of this rule is the reason why it's taking so long, and maybe if you break it up in this way, it'll take a lot less time. Do you know if anyone's looking at that?
No, I don't think. I think till now it's more like in the engineering side, like people try it out and they have this intuition that, oh, this rule, and then they just sort of throw it out. But I think some of the things could be automized. For example, you certainly know that when you have more variables, it really blows up.
Sure.
Right, so those things, but
I mean, I guess if you could at least know, I guess, like for this rule, it was this many groundings of this many functions, or this many messages were passed because of this rule, and then you probably see which one is completely killing you. I think that'd be kind of interesting.
Yeah, that's a good idea.
But that's just an engineering, like you're saying, that's kind of an engineering thing.
Yeah, I mean, you could certainly think of developing a theory, but I don't think anybody is, at least not in my knowledge. Yeah. It has been
prologue research.
I see. Yeah.
I think it's an unsolved
That would make
problem.
sense if people were doing it for prologue.
But I'm not quite sure.
Yeah.
I think it's an solvable in the general case.
Yeah. Yeah, but I think that's an interesting question, because it's interesting that sometimes people think that sort of doing inference for this is harder, but I think once you come to the domain of approximate inference, many of these things you do not really need to do exactly, and so that may really pay off because you're ready to sort of trade a little bit of accuracy for like good time and memory efficiency. So I don't know, some of these things may be applicable. For example, the thing that people tried in Prolog, but I'm not aware of. Yeah.
I think it comes down to estimation too. You said it, you don't need to do it exactly.
Exactly, yeah.
Because you're lifting, I don't know, I get a feeling like it's, to do exact lifting, it would seems to be equivalent to saying that two algorithms are equivalent, which we know is an unsolvable issue in the general case.
Right, so I think...
You're kind of taking a stab at it and making estimations and getting close enough so that you actually get good results.
I think it's different in the sense that lifting, as I described, it's exact in the sense it will give you exactly the same result, like provably the same result as BP. But I'm not doing two different algorithms though. It's the same.
But BP is an estimation.
Yeah.
So if you take, like you said, you take your Markov logic and give it all infinite weights, then you're equivalent to probabilistic logic, or I'm sorry, first order logic, and first order logic equivalent that proving that two terms are equivalent in first order logic is impossible.
Right. So I think that.
But you're fudging so you can actually get close enough where you're interested.
Right. So I think, but I think the sort of the place where this work comes in is saying that you could use resolution which is faster than propositionalization in first order logic. So it's a different question, what could resolution solve? So I think lifted BP versus ground BP is more comparable with resolution versus propositionalization and then doing inference. So what it is saying is that in resolution you could eliminate a lot of constraints, probably potentially infinite number of constraints in one step instead of really grounding them. It's saying the same thing. But it doesn't say anything inherent about the algorithm itself, as you said, right? In first order logic, I mean, even using resolution, some things may be hard, which again is true in this case. Yeah.
Which is why you brought up the case in passing that you could end up in a situation where you have to ground out the entire network.
Yeah,
because
exactly.
It's unsolvable. Yeah.
Exactly.
Okay.
Thanks.
Thanks, everyone.